that as long as you have a half-filled system, the physics of the repulsive Hubbard model and the physics of the attractive Hubbard model are qualitatively same. And how do we understand it? Because on naively looking at it, it looks like the physics should be very different, because in the repulsive Hubbard model, you don't want to have double occupancies on any side in the lowest energy state of the system. But in the attractive Hubbard model, you want double occupancies to be there at every site possible to have the lowest energy state, right?
Now I have a question.
Huh.
So for the p-type superconductor, we know that there is a two parallel electron coupled together and form the BCS pair.
Huh.
So is it connected with that kind of thing?
Okay, you are going very far. It is connected to superconductivity, but not necessarily to p-type superconductivity. Okay, because whenever you have an attraction between fermions, you can have superconductivity. If there is an effective attraction between fermions, they can form Cooper pairs, and that can lead to superconductivity if the Cooper pairs are able to condense. P-type superconductivity happens in special
I mean,
models.
two parallel spin coupled together, then
Right,
they
right. Then you have the spin triplet coupling, but here you have n up and n down, right? The attraction is between n up and n down. So even if they form a Cooper pair, it will always be in the singlet channel between up and down. It will not be a p-type pairing. It will not be in the up-up channel or down-down channel.
okay. That
Okay,
means they
Sajal?
form the S-wave superconductor.
Exactly. They can form an SF superconductor if they want, but at half filling. See, this property that a repulsive U Hubbard model is basically maps onto an attractive U Hubbard model. All this is happening at half filling, because other than that, there will be the chemical potential will not be U by 2, N will not be, the system will not be at half filling, then this equality doesn't hold. It's only at half filling that one can go from repulsive Hubbard model to attractive Hubbard model by doing this partial transformation, which is known as the partial Shiba transformation or spin polarized Shiba transformation, by doing a particle hole transformation only on one of the spin component. So now how do we understand that the physics of the two models, so differently looking two models, are connected to each other? So there is a very simple way to understand it. So in the repulsive Hubbard model, when you have this term, so what kind of ordering or what kind of order parameters you think can get stabilized in the system? So if your system has a plus u n up and down term, right? What can happen at half filling? At half filling, the most possible ground state is that I'm just drawing a ground state. You tell me whether it makes sense for you or not. I'm still thinking of 1D chain, although I'm not supposed to write it for some technical reasons precisely in 1D, but you can also think of 2D, let's say, just be more precise. And so on, okay? So this pattern goes on. So I'm proposing that the ground state of the Hubbard model with plus U at half filling should be something like this. Does it make sense to you? Do you agree with this? And this is just a pictorial representation. Of course, the actual ground state will look more complicated than this. But suppose compare this state with some other state where the spins are like this. So which one will have lower energy for the repulsive Hubbard model? Both of them are half-filled state because I have as many electrons as the number of sites.
Ma'am, for the alternative spin up, spin down have the lower energy
Why do you think so?
because
Okay,
the
I have
case
not
of
written the full Hamiltonian. Let me write, then it will be easier for you to explain. Right, now tell me.
because in the case of anti alternative spin up and spin down, there is
Hmm.
a no repulsive term.
There is no repulsive term. So, but in if I have all spins parallel, like up, 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 up,
Yes,
up, or
yes.
down, 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 then also there is no repulsive term. So
But
as long as I have one, go ahead.
if we think of the nearest lattice point, so
Uh,
as there is a same kind of spin exist for the nearest lattice point,
uh.
so maybe possible that there is a some kind of repulsion possible.
No, 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 that's not. You cannot think about a term which I have not written in the Hamiltonian, right? We are not trying to find out ground state of some very generic Hamiltonian which we have not even written. We are doing a simpler task of finding out the ground state of this simple Hamiltonian, which has a hopping term and a repulsive Hubbard term, right? So now you have to think only within this. So there is a hopping term. See, that's why I wrote specifically when you start talking about that the antiferromagnetic ordering should be closer to the ground state rather than ferromagnetic ordering at half filling. So Sitaram, do you want to give it a try? Just think of hopping plus U term and tell me which of these two states should be lower in energy. Of course, if I write
So,
something like
yes,
this,
ma'am, there is a another problem for hopping for the case of parallel spin,
uh-huh. What
because
is
it
that?
cannot, because for the case of parallel spin, the electron cannot hop to its nearest lattice point, because
Very good.
there is already exist same kind of spin there.
Yeah, so the hopping is basically eliminated by Pauli exclusion principle.
Yes, ma'am.
Yeah, but in this case, you can actually go to zero up down or maybe up down zero configurations. So even at half filling, it is possible to have a hopping within the system allowed if you have anti-parallel spins. So
Yes,
basically the system gains both from the hopping as well as the interaction term. Interaction term is basically same in both cases because there is no double occupancy, but then the hopping terms helps you in gaining energy or lowering the energy of the system if you have anti-parallel spins. So you should expect the ground state will must be having some kind of anti-ferromagnetic order, right? Now, what happens? So, how do I associate this ground state now having some kind of antiferromagnetic order with the ground state of the attractive U Hubbard model? Because I'm saying at half filling, the physics of the attractive U Hubbard model and the repulsive U Hubbard model are same. So, I don't need to study, both the models. If I know the physics of the one, I know the physics of the other. So, let us do a particle hole transformation. Okay. Somebody from somewhere I am getting some background noise. If you maybe use a headphone or something, it will be better. So suppose now I do the particle hole transformation on this type of state. So what I was doing is that wherever I have a particle, up particle, I was putting a hole, and wherever I have a hole, I was putting a up particle, right? So it means this state, if you look at here, I have a up particle, so I should put a hole. But here, along with down, I have no up particle, means I have a hole of up particle, so I will make it a up down. Similarly, this will become this and this will become this, right? If I do the particle hole transformation, that's what I get. Is it clear? Sitaram, is it clear to you? So now, does this state looks anywhere close to the ground state of the attractive U Hubbard model? What kind of ground state you will expect for an attractive U Hubbard model? Let me go to the next page and write on the attractive U Hubbard model. So you have the hopping and then you have this, right? Of course, along with the chemical potential term, which I'm not writing. So if since there's a minus U and the system is at half filled, means you have as many particles as the number of sites, what kind of configuration you would expect in the ground state at half filling? W occupied will be preferred, but since the system is at half filling, you cannot have W occupied at all sides. So what kind of configuration will be preferred? We have as many electrons as, but how do I distribute this completely? What configuration of this empty and W occupied side should be closest to the ground state? Very good. Now why alternative? Exactly. So if you have something like this, you gain from hopping as well as from the Hubbard U, right? So basically the ground state of an attractive U Hubbard model is what we call a charge density wave at half filling, a charge density wave. Okay, and the corresponding order parameter for this charge density wave is basically the difference in the occupancy of alternate sites. So I can say for 1D chain Ni plus 1 minus Ni. The expectation of the alternate sites gives you the charge density wave. Although what we saw for the Hubbard model, repulsive Hubbard model, the order parameter has the antiferromagnetic order in it. The ground state has antiferromagnetic order in it, and the corresponding order parameter is basically what? So it's basically Ni up minus Ni down. Uh, okay, let me write it slightly differently. So if you do a particle, so okay. So can you guess the form of the order parameter for antiferromagnetic ground state, which seems to be the possible ground state for half-filled Hubbard model with repulsive U by doing a particle Hall transformation on this operator? The particle Hall transformation we did to go from repulsive Hubbard model to attractive Hubbard model. So you will see that the two things are completely connected because I can just do a transformation here only on the up spin, you know, then it will become n up at I plus 1. But then the n down will remain as it is. And similarly, I do here n up at I and then minus n down at I, right? So this 1 and 1 gets cancelled. And what I have is n up I minus n up I plus 1, which means the magnetization at I plus 1, sorry, n up minus n down at I plus 1, which means the magnetization at I plus 1, and n up minus n down at I is the magnetization at I. So this order parameter maps onto, is it clear what I have written?
Ma'am, can
So it's
you
the over,
explain
sorry, tell me.
antiferromagnetic? Can you explain the antiferromagnetic order parameter? I mean, what you are
Yeah, yeah.
saying?
So what I'm saying is that, so is this part clear that for the attractive Hubbard model, this kind of configuration should be closest to the ground state at
Yes,
half filling?
yes,
And one can characterize this kind of ground state using an expectation value of this operator,
yes,
where you look at the occupancy of alternate sites, right? So if
yes,
the occupancy on alternate sites is different, that represents some kind of charge density wave in your system, right?
yes,
Now, we also saw that for the repulsive Hubbard model, the ground state was something like this, up, down, up, down, up, down. So what will be the corresponding order parameter? The corresponding order parameter is the magnetization on, say, first site minus the magnetization on the second site. And then it repeats, right? Is it clear? So I cannot use now the occupancy on the first side and the occupancy of the second side. That will give me zero, right? That is not the right order parameter to characterize this phase. The order parameter is a physical quantity you pick up such that it tells you the special property of that phase, of that state. So if I have to distinguish, say, this antiferromagnetically ordered state from this ferromagnetically ordered state, what kind of order parameter should I use? I should use something like this: Siz minus Si plus 1z, right? Now this order parameter will be 0 if I have ferromagnetic order, because it will be up, up, up everywhere, which means it will give me half, half, half everywhere, right? Sajanya, are you with me?
Yes, ma'am.
But
Just
if
for
you
the
have
background noise, I have muted.
Okay, I understand. But if I have opposite, I mean, if we have the antiferromagnetic order, then you get half minus half, half minus half, so it becomes 1, right? So this is the right order parameter for the antiferromagnetic state. Now, beyond that, what I'm saying is that just like, let me use the other board, just like we have gone from repulsive Hubbard model to attractive Hubbard model using particle Hall transformation on one spin. Similarly, we can go from the ground state of the repulsive Hubbard model to the ground state of the attractive Hubbard model using the same particle Hall transformation. Okay, because the attractive Hubbard model ground state will be characterized by so the repulsive Hubbard model ground state is characterized by this order parameter, and if I do a particle Hall transformation, this basically maps to I'm writing too many indices here. It's the link of the transformation, the particle Hall transformation between the two possible ground states is clear, or the possible order parameters is clear. So basically what I'm trying to say in short is, it might look confusing if you do it for the first time, that if you are sitting at half filling and on a nice bipartite lattice, or if you don't have any next nearest neighbor hopping, we do not need to study the attractive Hubbard model and the repulsive Hubbard model, because physics of the two models can be obtained just by doing a particle Hall transformation on one of the models. They are simply connected by a particle Hall transformation. So the repulsive Hubbard model with plus U maps onto the attractive Hubbard model with minus U at half filling on a bipartite lattice without any next nearest neighbor hopping. And the physics of the two model is connected. What I mean by saying that, so suppose I have a half filled Hubbard model on a nice lattice which has particle Hall symmetry. I know that the antiferromagnetic order should be there in the ground state. Now I can do a simple particle Hall transformation. So when I'm saying antiferromagnetic order is there, it means I have some this kind of ground state, and when I do a particle Hall transformation, I will get this type of ground state, which is actually the charge density wave ground state for the half-filled attractive Hubbard model. So the physics of the two models is just connected with each other by a simple particle Hall transformation. So basically they're just one model at half filling on nice lattice. Okay, but if you go away from half filling, there is interesting physics coming in attractive Hubbard model, which cannot be easily mapped on to the repulsive Hubbard model.
So we can say that for not in the half filling case, so particle Hall
Hmm.
symmetry will break.
Yes, there is no particle Hall symmetry away from half filling. Okay, and so once the particle Hall symmetry breaks, your chemical potential does not satisfy certain constraint like mu is equal to u by 2. and then you will see that you're in. Okay, this is probably the last board I could use. So if you are away from half filling, then you will see that your repulsive Hubbard model maps on to an attractive Hubbard model, but in the presence of a magnetic field. So, uh,
That means we have to trigger the system by some external thing.
what do you mean trigger the system?
I mean, we have to apply some external force or something like a time dependent thing so that we can transform from repulsive to attractive
No,
for
no, no, no,
not the half
no.
filling case.
For not the half filling case, I mean, I don't know about what kind of time dependent terms you are saying. That is very far from what we are doing right now. Okay, right now what we are saying is that only if the system is at half filling, there is no the Hubbard repulsive Hubbard model maps exactly to the attractive Hubbard model, and their ground states are also nicely connected. Okay, in one case you have the CDW ground state, which by particle hole transformation can be mapped to the ground state which has a non-zero antiferromagnetic order. But once you are away from half filling and you do a particle Hall transformation, you will see that the repulsive Hubbard model maps onto an attractive Hubbard model in the presence of a magnetic field. Because this term, see, how do you apply a magnetic field? When you have a magnetic field present in your system, that basically couples to the magnetic moment of your system, right? H dot M term you write. So here what you have is not a number operator, but you have the total magnetization operator. So basically the repulsive Hubbard model will map on to an attractive Hubbard model in the presence of a magnetic field in general. It turns out that that magnetic field is zero when you are at half filling. That is why the two models just maps onto each other and they basically become the same model. Okay, so the physics of repulsive attractive Hubbard model is same if you're sitting at half filling. Once you go away from half filling, different physics starts playing roles. And that difference basically comes with the fact that you can think of a repulsive Hubbard model as an attractive Hubbard model in the presence of a magnetic field. So basically you need to do the particle Hall transformation sitting away from half filling. So don't use the fact mu is equal to u by 2. Do the transformation without using it and then see what you get. You will of course get a negative u Hubbard term if you do the transformation only on one of the spin, but along with that you will get that the chemical potential for the up and down spins are different. Now, what it means to have different chemical potential for up and down spins, it means that there is an effective magnetic field acting in the system. That is what I am trying to convey to you people. Okay?
Okay.
So, as Sojourn, Sitaram, is it clear to you? Which reference I am following? So, actually, I am not right now following any book, but I will let me try to look for a book for you. If it is not clear, you can ask me now. See, if it is not clear to you, I don't think any book will help you in understanding it. Because book will be more complicated than my lectures. There is a book on Hubbard model itself. Let me give you a reference of that. I will just share the screen with you because you people are so much used to reading from book. Okay, I found the book. Let me show you. I have closed the Jamboard for the time being. So let me show you the cover page of the book. The title of the book is One Dimensional Hubbard Model. Do you see it? Are you able to see the screen I'm sharing?
Yes, ma'am.
So that this is a book on Hubbard model itself. And if you see, there is a chapter 2 about Hubbard model and its symmetries. Okay, so this book talks about the symmetries of the Hubbard model in all detail. As you can see, this equation 2.26 is what we derived, that the number operator commutes with the Hamiltonian. I mean, I didn't derive it, I asked you people to derive. I don't know whether you have done it or not. And the total spin operator commutes with the Hamiltonian. Then it talks about various permutations, translational symmetry, and then the momentum operator, more discrete symmetries. So see, this is the, you see equation 2.58 here. There is the operator, transformation operator JSH. This is the form of the uh, transformation one might use to go from to do a particle hole transformation. This specific form was given by Shiba, and that's why it is known as the Shiba transformation. And eventually it leads to the particle hole transformation, as you can see in equation 2.59, the kind of transformation we were doing. Okay. And then what happens under that transformation to the Hubbard model, all those things it will explain in its own way. I was doing it in my way simply. And they also introduced the spin operator in the bilinear form as I was doing. Okay, and then it also connects that if you do a Shiba transformation only on one of the spin, like it is doing only on the down spin in equation 2.8, what happens to the spin raising, lowering, and SA operators, and how it can be written in terms of the operators which are used to characterize the ground state of the attractive U-Hubbard model. So basically, it provides you a full connection between the attractive and the repulsive U-Hubbard model. I think it will be a good reference to read chapter 2 of this book. Okay. If you want to note down the title, you can note it down. It's a one-dimensional Hubbard model by Fabian Essler, Frank Gorman, Klumper, and Korpin. If you don't find the book, let me know. I have the soft copy, so I will be happy to share it with you. Okay. So go through the book if you really want to go through it. If whatever I'm saying is not clear, it is done in more. I mean, of course, the book will be more systematic than the lecture notes. I'm trying to give you basic feel for different kind of models like the repulsive Hubbard model, attractive Hubbard model, connection between these models at special symmetric points, connection between their possible ground states at special symmetric points and without away from those points. Okay, so what should we do next? I think you need some time to digest this part. So try to understand from this book, how the CDW order for the half-filled attractive Hubbard model maps onto a near antiferromagnetic state for the repulsive half-filled Hubbard model. So by the transformation, you can see it very nicely. In fact, one can also connect. So Saujanya was talking about superconductivity, right? So I mentioned only one uh, ground state, one possible ground state, which is the super charge density wave ground state. Just a minute. So are you done with that book? Shall I close that book now? The presentation. So the other possible ground state for the attractive Hubbard model is what Sojourner was talking about. So Sojourner mentioned about superconductivity. Now Sojourner has to tell me why does he think that in an attractive Hubbard model there should be superconductivity. What do you mean by superconductivity? So now we are not sitting necessarily at half filling. There is a special property of the attractive Hubbard model that at half filling superconductivity and charge density wave are degenerate with each other. Okay, so you can never make one of the phase more stable than the other until and unless you add some terms in the Hamiltonian which prefer one of the two phases. But only with these three terms in the Hamiltonian that I have written, that hopping, nearest neighbor hopping, attractive hue and chemical potential, the charge density wave and CDW both are regenerate. We will see that when we will come to the details of the attractive Hubbard model. But before that, let's first try to intuitively understand why this model should have any superconductivity, as Saujanya was saying. So Saujanya, tell us, why do you think this model should have superconductivity?
As there is just as the structure is basically charge density wave kind, so electron can hope electron hopping is possible and it can be anything. So I think for the
What's
movement of the electron, so it can be superconductivity.
No, Saujanya. So, charge density wave most of the time does not occur along with superconductivity. Okay, these are two competing order parameters. So, you cannot say since the system has charge density wave, it should have superconductivity. That is not the, I think that's probably some kind of uh, some thoughts you have in mind which are not you will see that technically they are not very correct. Okay, the CTW and super, there are many materials where you will see charge density wave and superconductivity both appearing, but either they appear for different parameters in the Hamiltonian or they appear on different sides of the lattice. Okay, so that they get phase separated, but most of the time they don't support each other, at least in this simple model. When you have charge density where is the ground state, then superconductivity is not the ground state. And maybe you can add some terms in the Hamiltonian, such that you start from charge density wave and then the hidden, the higher energy state, superconductivity state later on becomes more stable. But without tuning parameters in the Hamiltonian, both of them cannot support each other simultaneously. So what you are saying is that you have a charge density wave, right?
Yes,
Now, how will it support hopping?
because the first lattice side there is no electron, and the second lattice point is a two electron spin up and spin down. So the electron from the second lattice point can move to first lattice point or the third lattice point, and
See, first of
two.
all, this ground state which I am writing, zero up down, that is an ideal ground state which will happen only when there is no hopping term at all, when there is only a chemical potential, right? Once you have some hopping term, You will never have ideally 0202 kind of picture. You will have some
Yes.
n1, n2, n1, n2 kind of picture on different sides, because the hopping is going to reduce the order parameter from 2 to some finite number. But we still call it charge density wave because there is a difference between the consecutive sites occupancy. Okay, so you ideally won't have zero down, 0202 kind of picture once there is a hopping in the system. That is first point.
Um, or ma'am, can we thought of that the as the two in the second lattice point two electron in opposite anti-parallel spin, so they can
Hmm.
be coupled together to form the BCS Cooper pair, and there is a lot of lattice points, so there is a lot of BCS Cooper pair will be formed.
No, okay. So
Maybe to form
once
the kind of
we,
condensate.
yeah, so the two states, as I said, are very close in energy. So maybe your intuition in that sense is not that bad. Uh, so what is that S wave superconductivity? Is anyone else has any idea about it?
And when two electron of antiparallel spin coupled together, so that net angular momentum will be zero and the singlet state.
Right.
So
So
that,
we need to start writing from the possible ground state, right? Or the corresponding order parameter. So the order parameter for the CTW that we were writing, that just requires that the occupancy on the even and odd sides should be different, right? When this operator has non-zero expectation value, we call that the system has a charge density wave order. But when you think of a superconducting order parameter, then this will not be the right order parameter, right? What do you want? You want that this operator should have a non-zero value. Or actually even better than that, you want that the singlet operator should have non-zero value, right? Is it clear to you, Saujanya? Sitaram? Oh,
now
did
what
I
is the
lose?
meaning of the second term
Which second time? This one?
with the minus sign in the middle?
Oh, that's just a singlet, right? How do you create a singlet? I'm just creating a
Okay, right.
singlet. How do
Okay,
you create a singlet starting from a vacuum state? So C dagger up, C dagger down, minus C dagger down, C dagger up divided by 2 gives you a singlet, right?
yes, anti-symmetric.
Yeah, it just creates a singlet. That's how you define the superconducting order parameter. You have electrons in singlet channel which are bound to each other. So this object moves as one identity. The electron loses its identity and this singlet pair moves around in the system as a single identity. That is known as a Cooper pair. Okay, so now you see the difference between the order parameter for charge density wave. The charge density wave does not require any singlet pair formation or any pair formation for that matter. What it requires is that the density, the occupancy of alternate heights should be different from each other, right? But the superconductivity requires a very different order parameter. It wants to have singlet pairs. If you are thinking of the attractive U-Hubbard model, if you are thinking of a different kind of interaction in the system, where you have attraction even away from on-site terms in the Hamiltonian, then you can have triplet pairings or maybe D-wave pairings in the singlet channel. But right now you are in the singlet channel with on-site attractive interaction. So this is the only pairing kind of pairing possible, the simplest possible pairing. So of course there is an attraction between electrons on the same side. So you can expect we need to go to the BCS theory, okay? Until and unless people understand the BCS theory, they will not be able to appreciate why the attractive Hubbard model can give rise to superconductivity. But in this discussion, I'm not going to do the BCS superconductivity. I'm just trying to tell you that there is another possible ground state of the attractive Hubbard model, which is known as the S-wave superconducting phase, and that gets stabilized either by going away from half filling. So this gets stabilized when you go away from half filling, or you turn a next nearest neighbor hopping into the system. Okay, and this is most favorable at half filling. This goes away when you turn on next nearest neighbor hopping, but it can be stabilized further by adding a next nearest neighbor repulsion between particles. So the two properties are very different, but both of them are very interesting properties of the attractive Hubbard model. Okay, Sitaram, do you have any doubt about this, or Sojanya, or Sudeep?
No, I don't have any doubt.
Okay, good. Sitaram, are you happy with this discussion? So in next class, I will tell you how to obtain something called the TJ model starting from the large U limit of the Hubbard model. So what we have done so far, I defined basically the Hubbard model as a simplest possible model of metal insulator transition. I tried to intuitively explain to you what kind of ground states this model can have. Then we talked about the symmetries of this model. We did some interesting particle hole transformations on this model to understand some of the properties of this system. Okay, and to understand some of the properties of the ground state of this system. And we could also learn the connection between the attractive Hubbard model just by doing a particle hole transformation on the repulsive Hubbard model. So in next class, I will talk about the large U limit of the Hubbard model. It means when the electron repulsion U term is much larger than the kinetic energy, what kind of effective low energy Hamiltonian we can obtain in that limit, and what kind of ground states the system will have at half filling or away from half filling in the limit of U much greater than T. Okay, this is a very important limit to study. Of course, if we will also talk about U of the order of T limits, where one can do simple mean field theories and try to see what kind of physics will come out of the system. Okay, so next class we will do U much greater than T, and for this is what I gave you the reference of the chapter by Patrick Fazekas on Mott insulator. So that you should try to go through a little bit before the next class, so it will help you, or you can even do it after the next class. And today I will send one assignment by email, which will be mainly on the particle hole transformation or symmetries of the Hubbard model and things like that. Okay, so I will close the class now.
Okay, ma'am. Thank you.
Yeah. Sorry, do you have a question? Yeah, I will go to office actually just in some time because my this writing pad actually doesn't connect to my desktop somehow. So I have to teach from home and then go to office. Yeah, I will be there in maybe in another 10-15 minutes or half an hour, and the afternoon definitely I will be there. Okay. This reminds me that both of you need to put the title on that form which you gave me, and then only I can sign. Okay. So you can come around 3 to my office, huh?
Okay, actually, ma'am, we are going to your office and take your signature, then submit it to the coordinator.
Sorry?
Actually, ma'am, we are planning to go in the institute and taking your signature, then submit the paper to the coordinator.
Yeah. So that is why I'm telling that come around 3 to my office, okay? It's better to fix the time because I might not be there at that specific moment when you come. So try to come around 3.
Okay, ma'am. Okay.
Okay then.
Thank you.
See you. Bye.